I'm Shi Tang, came from National Yangming Jiao Tong University in Taiwan. So first of all, I would like to thank the organizer who organized such a wonderful workshop and inviting me to give a talk here. So today I will talk about how do we use a galaxy cluster to study the collisionless nature of dark matter. Okay, so in the standard cosmological model lambda CDM, where dark matter is cold and collisionless, it gives us a very good description about our large-scale universe. But on small scale, there are still some issues challenging this collisionless CDM model. For example, the cluster problem, where the CDM predicts that the mass density will keep on increasing towards the halo center. As you can see in this figure, the black dot line showing you this class P NFW profile. But some observational data from the dwarf galaxy or the low brightness galaxy shows that there are some flat cores formed in the object center, as you can see the data point here. So they have a shallower slope in the halo center. So there are this kind of tension between the CDM prediction and also the observational data is so-called a cluster problem. And there are some possible way that we can resolve this kind of problem. For example, the baryon process, that's the energy injected from the supernovae or AGN may redistribute the matter in the dark matter halo and decreasing the central density. Or alternatively, we can use the self-interacting dark matter model or the ASIAA model to resolve this kind of problem. So in this talk, I will focusing on using this ASIAA model as a compelling alternative. So this ASIAA model was first proposed by Spergel and Schneider in 2000 by introducing the elastic self-interaction of the dark matter particle with a non-negligible cross-section. So it was trying to resolve the small-scale issue, but at the same time preserve a very good description on large-scale predicted by lambda CDM. So in this model, the dark matter particle is able to self-scattering with this scattering rate given by this equation. So it depends on the cross-section, sigma, and also the local density rho. And the parameter here, the cross-section divided by the dark matter particle mass, is the parameter that we want to constrain. And in the right-hand side, you can see how does this ASIAA model can resolve this cluster problem. So here you can see different color refer to a different dark matter model, and it's showing you the density profile. So the CDM1 is shown in the red color, and all other color are showing the ASIAA model. So you can see with a larger cross-section, you will have a lower central density and form a larger core. So we want to constrain this cross-section value, and we can constrain it from the galaxy cluster study or galaxy scale halo. So from the recent study, the constraint from the cluster scale halo tell us that the range of this cross-section is about 0.1 to 1 centimeters square per gram. While if we use galaxy halo, we found that the cross-section needs to be larger than 1 centimeter square per gram in order to address this small-scale issue. So there's some tension between the constraint from the cluster scale halo and the galaxy scale halo, and this motivates us to extend the ASIAA model to have a velocity-dependent cross-section. So which means that the cross-section is not a fixed number. For a large-scale massive halo like a galaxy cluster, it will have a lower cross-section. But for the low-mass galaxy halo, it will have a larger cross-section. And in this talk, I will focusing on using a different approach to constrain this cross-section using galaxy cluster. So there have been several different approaches we can use. Like a typical way, we can measure the internal density profile. As I have shown you in this figure, you can see that how this ASIAA model will modify the density profile. And the recent study from Ecklet et al. 2022, they measured the central slope of this internal density profile from 12 massive exclusive galaxy cluster. And they compare with the numerical simulation from Bahama simulation, and they found that there's an upper limit of the cross-section is about 0.19 centimeters square per gram. And they also established the relation between these enlarged shape parameters as a power law function of the cross-section. So this will be useful to apply on other cluster survey if they can measure this density profile and then use this relation to constrain the cross-section. And alternatively, we can also base on the dark matter halo shape. Okay. So from numerical simulation, it shows us that actually the dark matter halo shape will also modify by this self-interaction. So the top panel is showing you the CDM case. So the CDM halo is more triaxial, and in projection it looks this elliptical shape. But if we introduce the self-interaction, you will find that the halo shape become much more rounder. Okay, so with a larger cross-section, you will have a rounder projected dark matter halo. And this is due to the energy and momentum exchange by this self-interaction and isotropized orbit of this dark matter particle. So we can compare this kind of analysis with the dark matter halo shape recovered from like a lensing analysis. So this is Peter et al. 2013. They compare this numerical simulation with the strong lensing analysis of a galaxy cluster MS2137. And they found that the cross-section with the maximum value of 1 centimeter square per gram can still consistent with the strong lensing analysis. But they also point out that the lensing analysis, we construct the projected survey mass density, so it makes this measurement less sensitive to the SIDM signature because of the projection effect. Okay, and thirdly, we can also constrain this cross-section by measuring the spatial offsets between the dark matter particle and the cluster member galaxy in the merging system. So we have seen a lot of bullet cluster analysis in this talk. So if we introduce the self-interaction of the dark matter particle, then the motion of this dark matter halo will lag behind the collisionless cluster member. So we can measure the offset between the collisional dark matter distribution and the collisionless cluster member distribution. And averaging a lot of systems, then we are able to get the statistical measurement. So for example, Harvey et al. 2015, they measured 30 this kind of merging cluster system, and they put a constraint on 0.5 centimeters square per gram for the cross-section. But later on, 2 years later, Whitman revisited their analysis and found out that the central position is not well defined in their in this 2015 work, so they revisit the analysis with a more accurate position measurement, and they relax the constraint to 2 centimeters square per gram. Okay, so recently we proposed another approach to constrain this self-interacting cross-section using the radial acceleration relation. Okay. So radial acceleration relation, which we call RAR, is a very tight empirical correlation between the total and the baryonic acceleration. So we can calculate the total acceleration based on this equation, based on the total mass measured from the rotational curve or the lensing analysis. And for the baryonic acceleration, we can measure it from the baryonic mass, including both the gas mass and also the stellar mass. And this RAR was first studied by Miguel et al. 2016. And this figure shows the result. So the y-axis is showing this total acceleration. And then the x-axis is showing you the baryonic acceleration. And at that time, they studied 153 spiral galaxies. And what they found is the data point in this acceleration space form a very tight relation. And this relation can be well fit by the equation shown in the left-hand side with the characteristic scale G diagram. Okay. And since then, a number of studies has been invested on this RAR using different galaxy samples. And all of this study confirmed this RAR relation. And they found that this relation is independent of the galaxy properties like the mass or morphology or the gas fluxion. And later on, in 2020, this RAR study was extended to the cluster scale halo. So the first work is done by Tan et al. 2020. They studied the RAR for 20 massive galaxy clusters in the CLASH survey. And this figure shows their results. So the y-axis showing you the total acceleration for this galaxy cluster using the lensing analysis. And then the x-axis is showing you the baryonic acceleration from the X-ray and also the stellar mass estimate. So what they found is those data points, these are the RAR from this CLASH cluster, is strongly deviate from the galaxy one, okay, which is shown in the black dashed line. And they also fit this data point with the same RAR relation that I have shown you in the previous slide and get the G dagger, the characteristic scale G dagger here, which again is an order magnitude higher than the galaxy one. So which tells us this RAR is not a universal relation that holds for all scale objects. And because this RAR relating the total acceleration and the baryonic acceleration, the total acceleration basically is determined by mostly from dark matter component. So it may tell us some information about the nature of dark matter. So we want to see if this RAR will look different in the CDM halo and the SIDM halo. So we use the Bahama simulation, which is the cosmological hydrodynamical simulation. And the advantage for using Bahama is it has the SIDM version, so it implements this dark matter self-interaction by Robinson et al. 2019. So we have the CDM and SIDM, and for each of these dark matter model, we can extract about 10,000 objects with a very wide mass range from the group scale halo to the cluster scale halo. So in total, we consider 5 different dark matter models: CDM, SIDM 0.1, SIDM 0.3, and SIDM 1. So here the numbers refers to the cross section. The larger cross-section we consider is SIDM 1. And we also consider the velocity-dependent SIDM model. So you can see this figure showing you the distribution of this RAR in different dark matter model. They're all quite similar, and what we want is the mean relation, which is shown in the purple colors. So now we extract this mean relation and plot them in the same figure, so you can see the comparison. So here you can see the different color lines refers to the mean RAR for different dark matter model. And you see there are 3 different panels because we split our whole object catalog into 3 different mass beam. And the top panel is corresponding to the high mass object, which is the galaxy cluster. And the middle panel corresponds to the intermediate cluster scale halo, and the bottom panel is the group scale halo. So now let's focus on the top panel first. Okay. So in the top panel, you can clearly see the deviation of this RAR from different dark matter model. For the CDM, it's shown in the red color, and then the larger cross section we have is SIDM 1, which is shown in the yellow color. Okay. So what we found is if you have a larger cross section, then the RAR will become more shallower and also flatten. Okay? And this flattering feature actually is due to the core structure formed in the SIDM halo, which will decrease the central density and therefore decrease the total acceleration in the y-axis. So we found there's a very strong SIDM dependency of the RAR at the high mass beam. And if you look at the middle panel, you can still see the differences between different dark matter models, but they are getting smaller. And if you look at the group scale halo, these RAR basically overlap with each other, so it's difficult for us to use them to test the dark matter model. So we found that there's strong SIDM dependency on the galaxy cluster, and we were focusing on the result on this top panel. And now let's compare this theoretical prediction with the data point. So in this figure, the solid line is the one that I have shown you in the previous slide from the theoretical prediction. And now the blue data point, the result from the clash survey done by Tan et al. 2020. So if you compare the data point with the prediction, just by eye, you can see that they are more consistent with the CDM and have a larger deviation with the SIDM1. Besides this mean value, we also compare the intrinsic scatter. So we found the intrinsic scatter from simulation is also very small and consistent with the observational result from Tan et al. 2020. And now we want to have a more quantitative comparison between the data point and also the theoretical prediction. So we calculate the chi-square value, which is just the differences between the total acceleration from the data and the total acceleration from the model, taking into account of the intrinsic scatter and also the measurement uncertainty. So for each of the dark matter model, we have their own chi-square value, and therefore we can calculate the p-value as well. So based on the p-value, we decide if this model is rejected or accepted. So what we found basically, if we include in the BCG regions in this cluster, we found that basically all the SIDM model can be rejected, and we are able to put the upper limit of the cross-section is about 0.1 centimeters square per gram. We also conduct another conservative analysis, is excluding the BCG data. And in this case, we can relax our constraint of the upper limits to about 0.3 centimeters square per gram. So both CDM and SIDM model 0.1 can explain our observational data set. So this analysis showing you the RAR could be a potential tool for us to constrain this dark matter cross-section. And you may ask, what is the difference between the RAR analysis and the density profile analysis? So from the density profile, you can see the deviation between different dark matter model happen within 100 kiloparsec. Okay. Beyond 100 kiloparsec, basically this density profile, they overlap with each other. Okay. And we repeat our analysis by applying a radial cut, focusing on this figure. So we apply a radial cut about 100 kiloparsec, which corresponds to a joint, stroke, and weak lensing analysis. And we found that even beyond 100 kiloparsec, we can still able to see the deviation of dark matter halo in this RAR. So the deviation in this RAR is more significant than the conventional class-corn features in the density profile at large radii. And in terms of RAR, if we want to test different dark matter model, we at least need to have this strong and weak lensing analysis. If we only have the weak lensing only data, then it's not possible to use this RAR to test the dark matter model. And more ideally, if we have the BCG data, then we can go inside this 100 kiloparsec and have a more tighter constraint on the dark matter cross-section. So recently, Tan et al. 2024, they conduct another analysis, is measuring the RAR for 50 BCGs in the manga surveys. And this figure shows the results. So the black data point are the new BCG data. And what they found is it's very consistent with the cluster scale RAR that they got from the clash survey, which is shown in the blue and the green color. Okay, so they have the same trend, and also they are significantly deviate from the RAR derived from the Field galaxy. And if we compare this new data set with the theoretical prediction, you can see that the orange colors showing the new manga BCG data, and they have a very good match with the CDM, and basically don't overlap with the SIDM in this region. So this is just a very preliminary result. We need to have a more careful investigation in this region. But it's showing us that this RAR could be a very potential tool for us to give a tighter constraint on the cross-section. So here I will leave you with the conclusion. And for our current analysis, we only based on 20 high-mass galaxy cluster in the crash survey. So if we have more cluster sample derived from the future sky survey for multi-scale lensing observation and X-ray analysis, then we are able to put a better constraint on this SIDM cross-section. Yeah, thank you, and I'll stop here and take questions.
I guess the ASIAA method works because the radial density profile depends on the dark matter properties, and the density profile is given by m of r cubed, and the gravity is given by m of r scale. So I guess the density, comparing the density is equally good as comparing gravity.
Yeah, we also thought about this problem, and actually we, instead of looking at the acceleration space, we also plot in the mass, total mass on the baryonic mass space, and also density. But we don't find such a tight relation. So it's still unclear why in the acceleration space we found such a tight relation.
Very interesting result. So the reference simulation that you used in this case is Bahamas simulation,
yes.
Right? It's only one baryonic feedback recipe. So
yeah.
How do you, what do you think the result will change? How much the result will change when you sort of marginalize over different baryonic feedback scenarios?
Yeah, this is a very good question. So this is the, I would say the limitation for this analysis, because we fixed on one galaxy formation model. And different baryon, in fact, would change the shape of the RAR. And we haven't checked this yet. So this is the plan we need to do in the near future to see how does the baryon physics will change the RAR shape.
Thank you.
Thank you.
Any other questions?
Thanks for the nice talk. Maybe I missed, but I think in the graph the velocity-dependent ASIAA model seems to lie between the 1 and 0.3, but it was surprising to me because velocity-dependent model is usually considered to have minimal impact in cluster scale. So can you comment on why velocity-dependent model, ASIAA model, are also showing difference in RAR?
Yeah, so let's go back. Yeah, so the SIDM model is shown in this color. So actually we have more parameter for the VDS IDM, and here we only fix with one VDS IDM. So this VDS IDM is trying to reproduce some observable we have. Okay, if we change the parameter in this VDS IDM, we will indeed change this RAR shape. We haven't checked. At the moment, we only have one VDS IDM model for this the simulation set.
Just looking at the slide, I'm wondering, is the shape assumed when during the weak lensing reconstruction of the clash cluster likely to influence the result of your analysis? Because, for example, they assume narrow frank white profile or some other flatter profile, could that just shorten the data and change the result, like saying, okay, this is not consistent with cold dark matter, but only because there's a systematic bias in the data or something.
Okay, yeah, so it's a very good point, especially here why we did this conservative analysis for the BCG, because in the clash survey, the total mass actually is extrapolated from the NFW. Okay, so the this high acceleration scale actually is dependent on the NFW model. And that's why we did this conservative test. But if you look at the new BCG data here, is independent of the model. It's basically computed from the kinematics. So it still shows a very good consistent with the CDM case.
Okay, thank you.
Thank you.
Maybe last question? Well, if not, let's thank the speaker again.